of species is a crushingly simple argument. If there's selection and if there is inheritance, there will be evolution. Darwin made that point in 1859, and what we've learned since then is that, in fact, his adaptation machine is much, much more effective than he ever dared imagine. So here are a couple of examples. We all know on the top is the famous Illinois corn selection experiment where over the course of 100 generations, corn down below is the production of milk in the United States from 1940 to the year 2000. The number of cows went down by about 60%. The amount of milk went up by about 40%. Cows are now producing 5 to 7 times more milk per capita than they used to in 1940. Most of that change is genetic. So we're sort of in an embarrassing situation, actually, because Darwin's adaptation machine, in fact, in principle, or at least in practice, in artificial selection, can work much, much better than Darwin thought. That's not just the case in artificial selection. Here's another example we love to teach in our evolution classes. This is the drought in the Galapagos where Geospiza fortis, as a result of a single generation of selection, evolved something like a single phenotypic standard deviation. That's a hell of a lot of selection, a hell of a lot of evolution. Do that for a few generations and you get a new species, right? So the situation is that things can evolve very, very fast when the conditions are right. And surprisingly, they don't do that more often in the following sense. These are data that were compiled by Gingrich, regraphed here by Estes and Arnold. What you see along the horizontal axis is the time difference between two observations of a trait in a species. This is a log scale, so there's 1 generation, 100 generations, 10,000, and 10 million generations. The vertical axis is the amount of evolutionary change between those two observations measured in phenotypic standard deviations. Again, on a log scale, there's 1 phenotypic standard deviation of change, 10, and 100. What you see is an awful lot of scatter, of course, but amazingly enough, even after extended periods of time, on the order of thousands of generations, the amount of change is a few standard deviations sometimes. And if you plot what we know can be sustained from artificial selection and actually from some examples in nature, the striking thing is that, in principle, natural selection can cause rates that are many orders of magnitude higher than what is seen over periods of 1,000 generations or more. That is to say, there's a huge gap of points that should be lying there if evolution was really doing its thing, as we know that it can. So what gives? My topic today, then, is why does evolution, in fact, work so slowly compared to what it might do? Now, the first obvious explanation is that selection in nature is typically not very strong. And I think that's the one possible hypothesis that we can reject pretty easily. Since the mid-1980s, there's been a cottage industry that's developed over measuring intensities of selection in nature. This is a review by Kingsolver et al. In 2001. These are selection gradients that have been normalized. So what this represents is the number of phenotypic standard deviations of change within a generation, the selection differential. And typically we see values that are on the order of 1/4 of a phenotypic standard deviation. If you team that up with a typical heritability of, say, 30% or 50%, you're going to get many, many standard deviations of change over the course of just tens of generations. So with that intensity of selection, again, we've got a paradox in terms of rates of evolution. So that's a non-starter. The second explanation, I think, has a lot more substance to it, and that is that selection is fickle. And by that, what I mean is that selection reverses direction frequently in evolutionary time. So obviously, if there is an oscillating pattern of selection, what will happen is that those reversals will cancel themselves out over some period of time so that the net amount of evolutionary change, the net evolutionary rate, is very much smaller than what is seen instantaneously over short periods of time. Now that explanation, which was championed by Gingrich back in the early 1980s and has been developed by a number of people since then, for which there's really great evidence from Mike Bell's sticklebacks. I am certain that that's a very, very important explanation for this pattern. But I don't think it's the only one. And the one I want to spend most of my time today talking about has to do with possibility number 3, which is that there is not enough genetic fuel to allow adaptation to proceed at high rates of change for long periods of time. So what I'm going to talk about now for a little bit is the possibility of evolutionary constraints. That is a famous topic of debate for the last 75 years in evolutionary biology between developmental biologists, paleontologists, and geneticists. I guess in the really trivial sense, it's obvious that there are constraints, right? So despite the many comparisons with Superman, not even our president has X-ray vision. There are an awful lot of things out there for which there is not variation, and so selection is just not going to make them happen. So that's an obvious, trivial observation. I think a more interesting question is genetic variation a limiting factor for things that do vary, that can be produced biologically? So that, I think, is a legitimate and interesting and not entirely understood question, and that's what I wanted to talk about. You might think that even that version of the question is a little bit silly, because we know that for almost any morphological trait, as a matter of fact, for every morphological trait I know of that has ever been selected on, an evolutionary response has been seen, and typically heritabilities for morphological traits, at least, are in the range of 20 to 60%. So lots of genetic variability is present for those kinds of traits. That view, I think, is biased, however, because it doesn't take into account the fact that what we've got is an organism with a whole lot of traits. And what I want to talk about for a little while is how a multivariate view of an organism changes our concept of how much variation there is. To motivate that discussion, I want to start with this equation. Don't worry, there's only going to be 2 equations in this talk. This is Landy's version of the multivariate selection response equation. And you'll notice, those of you who follow this stuff, that I've got funny little squiggles on top of the symbols, right there and there and there. And that's to remind me that what I'm going to now talk about are data that have been normalized by dividing all the measurements by the means of the traits. The reason I want to do that is because, well, actually 2 reasons. One is that whether 20 grams is a lot of change depends upon whether we're talking about a mouse or an elephant. And secondly, I want to be able to combine or think about at the same time traits that are measured in different units. So this is a way to normalize things. So this equation has got on the left a vector or a list of the amount of change per generation in a bunch of traits. And again, because of this normalization, those are proportional changes. And on the right, what I've got is a genetic variance covariance matrix of the traits and a vector or a list of the selection intensities, the strength of directional selection acting on those traits. And what I want to spend some time talking about now is whether genetic variation as described and capsuled by that genetic variance covariance matrix tells us something about limits to adaptation. It turns out that when we're talking about proportional measurements like that, we can decompose this genetic variance covariance matrix into the product of 2 other matrices. One is a matrix where along the diagonal are the evolvabilities. Those are the genetic coefficients of variation. The second thing is a matrix of genetic correlations. Now that's useful to do because we know that these evolvabilities are typically substantial. I mean, I can give you examples or quote some data on that, but typically genetic coefficients of variation are on the order of 10% for morphological traits, 5 or 10%. So I don't think that that's where constraints lie, if they do lie in this matrix. I think that they come in from these genetic correlations. And let me tell you a little bit about why we think that. If there is a pattern of genetic correlations that's constraining, here's what can happen. Up here I've got a hypothetical situation where there are 3 traits with equal amounts of genetic variation and no correlations, no genetic correlations between them. In that case, we can visualize the distribution of genetic variation as a sphere. That population will respond to selection in any direction equally rapidly. On the other hand, we can have a situation where patterns of correlation constrain the distribution of variation to a 2-dimensional plane within that 3-dimensional space. So in this case, selection can cause the population to evolve in that direction, but not in a direction that is perpendicular to the plane. In this last possibility down here, the most extreme one, all the variability is reduced to a single axis, a single principal component of variation. And I want to stress in all of these cases, which am I pointing with? In all of those cases, there's variability for each trait. So if we look at just one single trait, we see tons of variation. It's just that if you select on that one trait, you're going to get a lot of other things going along for the ride, and that may or may not be adaptive. So you can have correlations that reduce the dimensionality of evolution such that there's a limited number of traits that can evolve simultaneously. How are we going to measure this or talk about this in a quantitative way? Well, there are a lot of different ways that we can do that, and I think Gunther Wagner may do that, take us a little bit further down that road. But let me spend some time today talking about just one summary statistic that captures something about what's going on. And that's what I'm going to call the effective number of dimensions. Briefly, what I want to do is take that genetic variance-covariance matrix that's been non-dimensionalized and add up all the eigenvalues, the weightings on the principal components, and divide it by the largest eigenvalue. I'm just going to do that, okay? And I'm going to call that the number, I'm going to give that a fancy name, the effective number of dimensions, give it a symbol, n sub d. What does that represent in terms of something we can think about? If we have 3 traits, the effective number of dimensions can vary between 1 and 3. By that definition I just put up. If it's 3, what that means is that there are no correlations and the traits can evolve equally rapidly in all directions. At the other extreme, if all the variation is on one axis, the effective number of dimensions is 1. And if you can't quite visualize those in 3 dimensions, there you go. Isn't that fun? There's nothing new there. Just like to watch things spin on my computer while I'm sitting on airplanes. So what is the reality? So now what I want to do is show you some data. I collected from the literature data on multivariate variance-covariance matrices where a substantial number of traits have been measured. Here's a data set from beef cattle, one from Drosophila serrata, one from a fish. In all cases, we've got a fair number of traits that have been measured. Another kind of situation I was interested in thinking about was one that involves what I call infinite dimensional traits. These are things like growth trajectories and reaction norms in which individuals are described by a continuous curve rather than a list of numbers. The reason why I think these kinds of traits are interesting in the context of constraints is we can be pretty sure there's some evolutionary constraints here. And that's because we all know that no cow can grow from very small size instantaneously to a very large size. So there have got to be constraints underlying these kinds of traits. My collaborators and me and I for a number of years have developed ways to quantify genetic variation on these kinds of traits. And I'm sort of interested to see how they would fit into this picture as well. So I got a couple of data sets, one on mice and one on dairy cattle for growth trajectories. And in terms of the potential number of traits that can evolve for growth trajectories, the number is infinite because there are an infinite number of sizes, one for each age, that we can think about. So before I hit the button, does anyone want to guess what the effective number of traits is? I'll challenge you all to think deeply about this for a second. We have a 2. We have a... Is anyone going to say 42? No? Well, and so these are different kinds of traits. This involves eye diameter and back fat depth and a bunch of morphological traits, but scattered all over the animal. These are growth trajectories, so these are sizes at different ages. Here's the answer. The effective number of dimensions in all cases is below 2. So that's not very many. That's a smallish number. What that means is, what that suggests is, the world that we live in looks an awful lot more like that than it does like that. And I at least didn't know that before doing this. Maybe some of you did, but I think it is interesting in the sense that what that suggests is that an awful lot of variability that evolution can act on lies in certain combinations of traits, and other combinations of traits don't have much variation for them. What does that mean in terms of the response to selection? So one way we can look at that, at least in a theoretical way, is by doing the following. It's possible to calculate, if we put the effective number of dimensions on the horizontal axis going from its maximum, which is equal to the number of traits that are measured, down to the minimum. And on the vertical axis, we plot what the mean selection response is. What's possible to do is calculate what that number is if selection acts in a random direction or towards a random combination of traits relative to what there's variation for. So this is a theoretical exercise. I'm going to scale things so that we compare the response relative to what happens if there is no constraint at all. And what you see is that for 2 traits, these curves correspond to different numbers of traits. For 2 traits, as the effective number of dimensions goes from 2 down to 1, the average selection response decreases by something like 1/3. But the fall off is more and more severe as the number of traits goes up. Another way to look at this is to ask, what happens if we just focus on this worst case scenario where all the variation is concentrated on a single axis of variation? What happens? Well, it turns out that if all the traits are perfectly correlated, and if we make a plot of what the average selection response is as a function of the number of traits, you can get an analytic result. And when you plot it, here's what it looks like. When you get to 5 traits, you've lost about half of the evolutionary response. When you get out to 20 traits, you're down to less than 20% of the evolutionary response you get in the absence of correlations, and so forth. So these correlations then could be a real constraint to evolutionary response. All right. Now that's a theoretical answer to the question, but now what I want to ask is there data that'll let us see whether in fact these correlations make a difference or not? And to, excuse me, to look at that, I'm going to consider 4 case studies. The first is from a classic piece of work by Dolf Schluter. Dolf reasoned that we know from quantitative genetics theory that if you have 2 traits, we're plotting the means here on these 2 axes, if we start with a particular combination of those traits, and now we select them towards a new optimum, what quantitative genetics theory tells us is that the initial response that evolution will have is along the axis where there's the most genetic variation, the first principal component of the genetic variance covariance matrix. And that's what Dolf referred to as the genetic line of least resistance. So that's the initial evolutionary response. And then what happens over time is that the population deviates from that axis and makes a curving trajectory towards its ultimate target. So as time goes on, we predict that this angle between the axis of least resistance and where the populations evolve to will grow. Dolf tested that prediction by analyzing data from 5 taxa of vertebrates, looking at the variance and covariance matrix in one of them, and then looking at the difference in the means between closely related populations of species. And I mean, this is one of these things I can't believe actually worked. What he found is that as time goes on, evolutionary time proceeds, the angle between the axis of least resistance and the evolutionary response, in fact, grows as predicted by the theory. This is, in fact, Ney's genetic distance, but roughly speaking, Dolf reasons that that's a period of about 4 million years on average. So what this is saying is that these genetic correlations are having an impact on the evolutionary trajectory of these organisms over substantial evolutionary times. Here's a second study that I think has much the same message. This is from Dave Houle and his colleagues. Dave assembled or measured a lot of Drosophila melanogaster wings, estimated the variance-covariance matrix for landmarks on those wings, then asked, what is the relationship between variation within this species and the wing shape in a bunch of other flies? That is to say, are these flies divergent along the axes or along the trait combinations for which there's variation, or is natural selection oblivious to that and it's taken these flies into directions that are independent of the pattern of variation? What he found, oh, by the way, here's the phylogeny of these animals, and we're talking about phylogeny that goes back to something like 40 or 50 million years ago. So we're talking about, again, pretty good chunks of evolutionary time. He did the statistical analysis a little bit differently than the effective number of dimensions that I just mentioned, but to give you just the flavor of the results, if you ask how much variation is there in the direction separating these two species phenotypically relative to how much genetic variation there is in some random direction, what you find is that for all comparisons between Drosophila and these 7 other species, there is much more, so that dashed line is sort of the null hypothesis if selection causes species to diverge in directions that are at random with respect to the genetic variation. In all cases, the genetic variation, the direction of divergence is along the axis where there's a lot of variation. And in some cases, it's very close to the solid line up there, which is the axis along which there's the maximum amount of variation. So bottom line, again, is that there's a pattern of correlation that's impacting the direction, phenotypic direction in which evolution is working. Let's see. I've got 5 minutes. I'm going to compress my description of this interesting study by Mark Blows and colleagues. They showed that this is sexual selection on cuticular hydrocarbons, 8 cuticular hydrocarbons. And the bottom line there is that within a generation, the direction of selection, the combination of hydrocarbons that are being selected, is almost at right angles with respect to the axis where there's genetic variation in this population. So there is something like only 1% as much variation in the direction that selection is acting compared to the maximum amount of variation. The last empirical example I want to draw your attention to is from a study of genetic variance for lifetime fitness, not a morphological trait, but fitness itself. We've got a number of species in which it's now been possible to estimate genetic variance for fitness. Here are 2 of them, the collared flycatcher and the red deer. They have substantial evolvabilities within males and females for lifetime fitness. These 2 species also give us estimates for something I find very interesting, which is the genetic correlation between sexes for fitness. So check this out. The genetic correlation for fitness between males and females in that bird and in that mammal are highly negative. Now, there are huge standard deviations associated with these estimates, so I don't want to get too hung up on exactly what those values are, but I find it very striking that in the 2 examples that we have, the suggestion is that adaptation in one sex causes maladaptation in the other. All right, so where does this leave us? My conclusion from these data is that genetic correlations can very strongly bias the direction of evolution over millions of generations, and they can substantially decrease the maximum amount of evolution that happens, the evolutionary rates. But even if I really try pretty hard, it's difficult for me to convince myself that the constraints imposed by these genetic correlations, according to the data that we now have, are actually limiting evolutionary rates in an absolute sense. That is, if we go back to this plot, and here's my original extrapolated evolutionary rate on the basis of artificial selection experiments, genetic correlations may be able to knock that maximal rate down by 1 or even 2 orders of magnitude, but that still produces an evolutionary rate that if we extrapolate it out to something like 100,000 generations, is much greater than what we see typically in the fossil record. So I think that these genetic correlations are having a big impact here, but not out here. The last thought I want to leave you with today is that there is a fourth mechanism that I think is important in limiting evolutionary rates that has gotten way too little attention, and that is the possibility of a Malthusian speed limit. So this is an idea that a few people, including Doug Futuma, Richard Gammelkiewicz, and a couple of others have started to think about, but I think it really is one of the big gaps in our understanding of evolutionary rates. And the point is simply this. If we go back to thinking about a situation where there's a little genetic variation, a soft constraint, if you will, a second factor is that demography may also play a role in evolutionary rates. And I'm thinking now about hard selection. Here's that example I talked about early on from Darwin's finches. We got a lot of evolutionary change there in a single generation. But if you look at what's happening to the population at that time, it's a total disaster. This is the number of finches over the time course where that evolutionary change happened, and the population is crashing from 1,400 individuals down to 200 individuals. That's not sustainable. It's genetically sustainable, but it's not demographically sustainable. So I think one of the really big challenges, one of our really big holes in understanding evolutionary rates is understanding what the ecological or demographic limits for sustained evolutionary response are. It may well be that you can evolve real fast in the short term, but those populations which do so are doomed to extinction. And I would love to know what are the ecological properties of species in terms of population growth rates, resistance to catastrophes, and so forth, which allow some species to sustain long periods of rapid evolutionary response and others not. Thanks very much.